Hello again everybody, once again welcome back to the desk in the 11th episode of this series on electronics for model railways. Today we are back at the desk with a bit of theory. This is going to be building into something a little bit bigger. Ignore this, we're not looking at this rather nice little touch screen today. Looking at is this, a rotary encoder. This has all come about because of Chris over at Wire and Wood and his knob box. So here we have a knob we can twiddle. We're going to have a little look at one of these today. So, let's get on with it. So first off, twiddling knobs. Traditional train controller, which I'd show if I actually had, but I don't. You all know them. You have a dial. You twist the dial. You turn it one way to make the train go faster, the other way to make it go slower. Or it's got a centre point, one way backwards, one way forwards, and there's a switch. Traditionally, they use a potentiometer, which is a resistor you can vary the value in. You've got about 300 degrees of rotation on those. They don't go all the way around. I don't have one to hand, actually. Yeah, and I don't actually have any to hand. I've got some somewhere. I don't quite know where. But that's got a memory. So say if you turn your device on, if this was a thing, you turn it there, and maybe that's 50% speed forwards. Turn your controller off. Train stops. Turn your controller back on. Train is going at 50% forwards. Not always desirable. Sometimes it is, but it's not always. Say you want to use this dial to do 2 or 3 different things. Maybe you're going to. I want to set a train. I want to set that train running. Now I want to change to another train. Well, this is saying you're at 50% speed. So what happens? Well, that train's going to jump away at 50% speed unless you go, oh, very quickly, turn it off. Or you have to stop one before you go to another. Or you need some other switch that says, ignore this while I reset it. A little bit of a problem. This little thing works a bit differently. See, a rotary potentiometer, you turn it and it varies a resistance value. So it's setting a value. This doesn't. That, exactly the same as that. What this thing does is generate pulses as you turn it. So it's encoding the rotation, sort of, hence the name. And what it does is it lets you determine which way you've turned it, and also how fast you've turned it. So, yeah, you can sort of set your speed, and off you go. This one we're going to have a look at how to connect this to an ESP32. Spoiler alert, I've already connected it, as you can see with these orange wires. It is quite simple. These things work in a slightly strange way. So the first thing we're going to do, a little look at how they work. So I should be back in a mo. Okay, so what is a rotary encoder? Well, what you've got inside it, there's a wheel. Can't quite draw the wheel straight because there's bits on the board underneath anyway. And that has got a bit in the centre, and that goes off and is connected to one of its pins, and that's connected to the centre pin. And on one side it's got bits like this. There's loads of them. So the number they have on them varies. So I think the ones I've got about 20 on a side, and those are all connected to the middle. And critically, there's another set of that on the other side, but it's offset by half the distance, or a bit of the distance. So behind it, there's another one that's like that. And then on this side, there's a wiper, which goes to A, and on the back, there's a wiper that goes to B. And it's basically 2 switches. As you turn this thing round, it'll connect, either A, B, or both, or neither, to this centre point. And what you get is this. Just move that so we can see it all, or see most of it. So at any given time, this is your centre pin, and these are the 2 other pins you have, and they're either connected to the ground point, which is when they come down here, or they're not. You have to pull the things up. So come back to this side. What you have to do is these pins here go off to your microcontroller, like so. But you need to put a resistor onto each of those, which goes to your positive voltage. 10k is sort of normal value for this. So what you have is each switch is either, and these are just normal switches, they're just arranged in a circle. I'm trying to get a bit of paper to sit on my desk. Yeah, it's either connected to both or it's connected to none. And as you turn it, this moves. And what you find is that's one state, and that's another. And as you turn it, it clicks. Click. Click. But between the click, there's some other states. So it starts here. Hi, hi. And you go, hi. Yeah, so I'm flicking my pen around. If you turn it a little bit clockwise, it'll go there. Ah, well, it's now reading 1 0 because you've got a 1 and a 0. And then it goes here. And now you've got 0 1. No, sorry, 0 0. Let's get this right. Then it goes there. Then you've got 0 1. And then you're back here and it's 1 1. So going clockwise, you've got a sequence. It starts on 1 1. Goes to 0 1. Goes to 1 0. Sorry. Let me get this right. Starts on 1 1. Goes 1 0. 0 0. 0 1. And then it loops back round again. But if you go anti-clockwise, it starts on 1 1. And it goes 0 1. 0 0. 1 0. And then that loops around again. And you get all of these different readings. And as you can see, if you look at any given reading, you don't necessarily get a lot of information out of it. But if you read one of the pins, say you read that pin, always look at the first pin. Right, so if you're looking at that all the time, you can work out what you're doing by what the value of the other pin is, because you've got a set state. So what you do is you monitor those and away you go. The interesting bit here is only one of these bits changes at a time. You don't go, hence why I was messing around at the top, you don't go 1 1 to 0 0. If you ever see 1 1 to 0 0 when you're reading it, you know that or that was in the middle and you've missed it. But you don't know which one. But you do know, well, I'll just discard it. The thing's turning too quickly. And you can get these things. I'm using them here as a knob that you twiddle. You can actually get these things that sit on shafts, and they can be used to give you the shaft rotation. And if you manage the time between these pulses, you can get the speed, which is quite nice. So how are we going to wire this up? Well, as I've said, it's fairly straightforward. The device itself typically comes as a sort of a box. It's got 3 pins one side and it's got 2 pins the other side. We're not going to use these two this side. What it actually is a switch. So normally they're not connected. Press the knob in the middle and those two are connected. It's just a very simple push switch. Usual is you connect one side to ground, you connect the other side to a supply through a resistor, and then there you can take an output. There are some boards you can get that have got these things pre-built on them, KY40s I think they're called, where you've got a ground supply, a positive supply, then you get the 2 output pins and the switch pin, and they've got some circuits on them. Up here, again, goes to ground, and like I say, you connect those to your microcontroller. Now you can, and I have done in the past, put a 10k resistor on here directly. We're not going to. We're going to use the input value on that. So let's get back to the little board, have a little look. And as you can see, if if we ignore the screen and the fact it's lit up, these two orange wires, and I've got them going into pins 16 and pin 17, go to any digital pins you like. ESP32, have a little look and see what the pins are. I could have put them over here on 20 and 21. They are the I2C pins for the PCF 8574 or whatever, 85 whatever. Yeah, that chip I looked at the other week, and other things. So I'm leaving those free. These two were free on this side. There are some others which you don't use these three on the end. I could use that pin there, for example, pin 4. It does things at startup, so you can use it. Need to be careful, but I'm avoiding it. That's the wiring we've got. Well, okay, so that works. Now what we're now going to do is have a little look at the code we need to make this work. Fairly straightforward. So the first thing we're going to do is we are going to tell this piece of software where it's connected. That'll do. Very, very simple. The next thing I'm going to do, and because this is a fairly standard thing for me, I'm going to put that bit of code in, and then in the loop I'm going to go in and I'm going to put that. And this gives me the clock function. This is just simply every time I go through this iteration, I've got a timer available to me. It's useful if you say I want to update the screen every second. You've got a way of doing it that doesn't involve pausing. We're also, because this is how we're going to get the output on this one, going to put this in. So this, as we saw in the episode on serial communication, starts the serial port up, and we are going to then find a little bit of code to start with. We're going to do that. So we're going to set up these two pins, which we've defined up at the top for the encoders, as inputs, and I'm saying I want to use the internal pull-ups. So they've both got a 10k pull-up, and then finally we're just going to say hello. So before we do anything else, I'm going to upload that and we're going to have a little look. Now this is not going to be a terribly impressive sketch, it must be said. This is really just to check and make sure it works. So as that uploads, resetting via the pin, we're going to go into that serial monitor, I'm going to press reset. We get the usual junk that the ESP32 kicks out at startup. And there we are. Hello, Rotary Encoder test. That is now working. Okay, so that works. What's going to happen next? Yeah, let's build this up and just let's go through this as we're doing this. So to start with, I'm not going to put a delay in here. So we're just going to run this at full speed, and I'm going to show you why we want a delay in it. So to start with, we need a value. This is where we are going to store what we're getting out of the encoder. So encoder value equals 0. Get rid of that v, equals 0. And we're storing 2 pins. So every time we do a cycle, I'm going to go encoder value equals 0. Put some spacing in, just make it a little bit easier to read. And what I'm now going to do is put both of those pins into that value. So I'm going to do that one, and I'm going to do that one. So at the end of this, what we're going to have is it's an 8-bit value. I think I just said it was an 8-bit value. Yeah, it's an 8-bit value. So that is going to be in binary 1, 2, 3, 4, 5, 6, 7, A, whatever that one was. This is then going to go again in binary 1, 2, 3, 4, 5, 6, B, and at that point we're also going to have A in there. Oh, let's see what happens with that. Now, obviously, what I don't want to do is throw that to the screen continuously. So what we're going to do is if d now minus... let's have a think about this. The time now minus... yeah, right. I just need to get my head around this one here. We need another time up here, which is going to be uint 32d t last update equals 0. 0, that'll do. So what we're going to do here is if the time now minus the time of the last update is greater than 1,000, so this is going to be as more than a second passed. If it has, what we're going to do is serial print line enc val. I'm going to take you to do it in hexadecimal. It's only ever going to be one number. It should be 0, 1, 2, or 3. It should be all we get. Let's upload and have a look. And what this is going to do is confirm we're actually reading the things. Ooh, there we go. T last update. Uint 32t. Get the timing right. The text right. Here we go. And this is just going to give us a basic read of the encoder. So go into here, clear that, clear it again, and we're just getting a... Okay, I've got something wrong in my little timing loop here. D now minus that is greater than 1,000. Yeah, there's something wrong in that little loop because that's not working. Ah, yeah, I know what the problem is. T last update equals T now. Right, rerun that. And we're going to come back to why that was showing 3 so much. 3 being binary 1, 1. So while that's uploading, well, it'll finish that, kill that. 3, 3, 3. See, that's running better. Now if I'm holding that part way between a value. 3, 0, 3. But that's reading, and what that's showing is we're picking this thing up. And if we look back at this bit of paper, we're seeing 3, 2, 0, and 1. So we're actually seeing the values we want. And this sits, and each time it sits in one of its little slots, it's picking up a 3. Well, that's... Okay, so we're reading it. I would be the first to admit that's not terribly useful as it sits. And it's interesting, what we don't actually want to know where the thing is. We don't really care. What we want to know is what's it done. So what we're looking at, I'm just going to make a little note up here because it's a bit easy to see. What we want, these are the sequences. We want to see 1 1 1 0 0 0 ding ding, or 1 1 yeah, just fat fingers. Anyway, we get there. 0 0 ding ding ding. What we actually care about isn't the numbers. What we care about is the arrows. We want the transitions. So how are we going to get the transitions? Turns out it's actually quite straightforward. What we do is we come down in here, and instead of saying that encoder value is 0, I'm going to say equals 2. Okay, so what the hell does that do? That is a bit shift operator. So we're going to start off, say we come in here and we start off with a binary number 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that was our previous value. This is the 3. So we're going to come in here and we're going to say, well, that encoder value is that. I want it to become this. B 1 2 3 4 5 6 7 8, and that's what that operator will do. It literally moves everything 2 spaces to the right, and it pads the lower end with zeros, which is quite important. We want the lower end to be zeros. So we're now going to come through and we're going to run this, and when we get to the end of it, we've actually now got a 4-bit number. Now we have to watch out because I always want the top bits to be 0. So what I need to do is then there's one more line, which is encoder value gets ANDed with XOF. And what that's doing, come over here, that is basically ANDing it with this. It would be 1 2 3 4 1 2 3 4. Now logical AND operator says it's the same as the normal AND. If both bits are 1, the output bit is 1. So by setting these bits as 0, what I'm doing is saying those bits in the output must be 0. And by setting these as 1, it'll be, well, whatever it was before. So I've now got a 4-bit number in here. And I could decide, well, what do I do? I mean, let's run that, and we'll see what these 4-bit numbers look like. Because this actually has some useful information in it as well. 4-bit number, there are 16 possible values, 0 to 15. Because obviously it starts at a 0, which is that's something else to get your head around. If you're going to start using these things, you need to get your head around that. So F, 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 F. Hold it slightly, get a different value. Goes around there, so slightly again, we get different values. Turn it the other way. So we're starting to get, we're getting a couple of different values in there. Not as many as we could do. We're not getting all of them. So what we need to do now, and we do it here, because we're getting a lot of values. Don't forget, we're getting a lot more values. I'm just showing this every so often. We need to decide, what do we do with this stuff? Well, there's actually something we can do with it. What we've got, I've got this as another little printout, so I'm going to shift this out of the way again. I'm going to bring this in. We've got a little bit of a truth table. Does it go up a little bit? You might be able to see that a little bit more. I would have put this on screen, but I forgot to save it. So over here, we've got the values. Now this is the old values, the first 2 digits. The new value is the second one. There are 16 possible combinations. Now the rules are quite simple. If the first 2 bits and the last 2 bits are the same, we haven't moved. So we've got 4 situations where that happens. And the direction, well, it's not applicable. We haven't moved. We then have some valid movements. So we go from 00 to 01. Yep, that's valid. We've moved clockwise. Or 00 to 10. Yep, valid. We've moved anti-clockwise. This is what I said. If 2 bits have changed, that's invalid data. We don't want to do anything with that. We can't say that will never happen. It will happen. But we need to do nothing about it. But we don't move. And this goes through here. And what we've got is 4 occasions where we go anti-clockwise, 4 where we go clockwise, and a whole load where nothing happens. We could do something with that. We could say not applicable is a 0. Clockwise is a 1. Anti-clockwise is a -1. So we carry on and we do this all the way down here. 1, 1, 0, 0, -1, 0, -1, 1, and 0. And if we had, say we have a number that we're going to try and control, the speed of our train maybe, or the volume of something. Well, what we can do is, as the thing increments, we can either add 1 to it, or we can subtract 1 to it. But how are we going to do that? It actually turns out there's a bit of a cheat, but it's quite simple. Let's knock my microphone again. Just realign the camera a bit. Yeah, anyway, that's going to be slightly angled. But anyway, what we need to do, we could put in here an if statement. So if we've got the value 0, do such and such. If we've got the value 1, or else if we've got the value 1, do this. And And we could go in and we could just do that for the 8 values we want. Yeah, there's another way of doing it. What we're going to do is I'm going to go back up to the top. As you can tell, I'm copy and pasting this in from somewhere else because I've already written this. So we're going to come up here and I'm going to put it, it doesn't really matter where, I'm going to put it there. And this is an array. So we've got 16 values, which if you remember our little pattern, 0, 1, -1, 0, yeah, and it goes all the way along here. So we can actually say, in this little printing value down here, I'm going to print the encoder value, which is that hex value, and we can also have an output value. So let's create one of those. And I'm going to go here. I'm going to make this one a bit bigger. Uint 16. Sorry, int. I want this to be able to go negative. Int 16t. So that's saying I want a signed value. So that can go from minus 16,000 up to plus 16,000, I think it is. So here we go. We're in this point here, and we're going to go. We're going to say O plus equals, and this is here we go here. Table, which is what we called it. Enc val. So what's that doing? That is saying go into this table, which as you see we've got the defined at the top. If our encoder value is 3, the value is 0, so we're going to add nothing. But we've got these values in the middle. So what I'm then going to do, I'm just going to make a slight change here. Stop that printing that. We're going to go serial.print. I'm going to put a couple of spaces in. And serial.print ln. Oh. It's very helpfully putting brackets around things for me, which is, it's going to be capital O. Let's see what that does. As this uploads. The serial monitor, I'm going to kill that. I can start rotating it. A little bit interesting, but it is rotating it. Well, let's modify this little bit down here now, because I actually want to see all of what this is doing. So I need to come up here. I need int 16t last O also equals 0. That was the previous value. So now instead of this update, what I'm going to say is if O not equal to last O. So if it's changed, do that, and then at the bottom, last O equals O. Run that. Now it's worth noting there are libraries you can get that can handle these things. You can have some problems with them. The libraries make assumptions. So you need to know what those assumptions are. Some of them want external resistors, some don't. Some want capacitors, some don't. Yeah, so here we go. Now that was one click. That's generated all of that. Why make this a little bit bigger? Right, I'm going to click it one click clockwise. Okay, it's generated quite a bit. But the interesting thing to note here, we've started with a value of 5. Then we've gone 6, then we've gone back down to 5, then 6, 7, 8 for one click. Okay, so do another one. 9, 10, 11, 12. Do another one. 13, 14, 15, 16. Let's turn it back down again. And it goes back a little bit. Oh wow! You see, I mean you see the problem. This here is now it's going like the clappers. But there's a fairly interesting pattern. Let me just click it this way again. Clockwise ends with a 7. Clockwise ends with a 7. Clockwise ends with a 7. Go the other way. Anti-clockwise ends B. B is 11 in hexadecimal. A is 10. Kill that. Went to B again. Look at that. A huge amount of nonsense, but it's a B again. So actually, if you look at this, what if instead of incrementing on all these other different values in our little table up here, what if we only increment on 7 and 11? Let's try that. Because what we can do is we come up here, put a different table in. I'll get rid of the word static. I don't need that. That's from an experiment earlier. I'll comment that one out. So, clear that. Let's try that. And this is the other advantage of using this array. That is literally all I've had to do to change what this does. I could go in here and say, I don't want that to be plus or minus 1. I want that to be plus or minus 5. And that would work. I'm not going to just yet. We'll have a look at how we can do something like that in a minute. But let's have a look now. So, there's a few clicks. So I'm going to start with 1 click clockwise. Another one. Now that's only 1 click, but it's registered twice. Another one. Another one. Another one. Yeah, B. B's going the other way. I didn't turn it the other way. So again, we're bouncing. And if I go back the other way, that's 1 click. That's another click. So, as you can see, that, I mean, it's working in a way, but it's not useful. It is uncontrollable. So you think, well, how on earth do we use that? And what we're going to look for is a little pattern. What I'm going to say, and this is just the way I'm going to do this. To start with, we are going to go in. I'm going to put a little delay in here, and we'll see what difference that makes. So I'm going to go into here. I'm going to start it here, and we go if t now minus t last action. I'll have to define that. Is greater than 1. Do something. And the printout bit I'm not bothered with. That'll just run. So we'll take all of that and we're going to put it in there. Now what that's going to do is say there's got to be at least a millisecond between reading them. So I'll come up here and I'll go uint 32d t last action equals 0. And have we got in here, the one thing I need to do now is say, well, we've had a last action, so t last action equals t. Now, let's try that. This is basically what this is doing. The ESP32 runs at 80 megahertz, so 80 million cycles a second. And every cycle it goes through its programming loop, it's trying to read these things. Now, obviously, the instructions take a little bit longer than that. So it's not actually doing this 80 million times a second, but it's getting there. So now, you see we're getting 1 value. Oh, no, and then we got 2. 1, 1, 1. And you might think, well, actually, well, I mean, you've just fixed it. That works. And yes and no. So let's see, I'll just turn that. See, it's working. Turn it a little bit quicker. That works. Turn it back down. That's not bad, but see there, it went down, it jumped up. So carry on with that, see if it'll do it again. It'll do it every now and again. And how often it does that depends on the switch you're doing. And you'll be doing this and it will infuriate you. See, there's another one. Can we do anything about that? Yes we can. So what I'm going to do, I'm going to come up here and instead of doing that, we can do that in a minute. I'm going to have another one here. I'm going to go int 8t, another little value. I'm going to call it v, and it is going to be this table lookup. Val. So that's now a 1 or a -1. Or a 0. If it's a 0, I don't want to do anything. So we're now going to go if v is not 0. because if it's 0, I don't care. What I want to know, and what I want to pick up, is multiple pulses of this in order. So we're going to look at, well, what are we doing now? What did we do last? Because if you look into this little string here, we've got 1 going the other way. Well, if I say these 7s, if I say I'm only going to move if this value is a 7 and the previous one is a 7, or if it's an 8 or a B and the previous one is a B. So in this case here, what we'd say is, oh, that B, I'm going to ignore that B, and I'm also going to ignore the 7 after it, but then we'll carry on. And it's a way of rejecting bad information. So I've got V. I now need to come up here. I need another one, which is going to be int 8t last V. Because we've got to let's put them up at the top. There is another way around it. You can declare them down here and say it's static, and then it won't change, but it's easier just to put them up at the top. So in this loop, so we now know we have a value, and it's a 1 or a -1. So now I'm going to say if the last value equals the current one. Right. In there, we've got a valid number. So I'm going to move that into there. And then regardless, we're going to go last val equals V. And that has to be in this loop, because otherwise what's going to happen is most of the time V is 0. Or this table is returning a 0. So unless we're very, very, very quick, we're never going to get anything out of it. But this way, fill some of these blank lines, this should now work a little bit better. So let's try this one. And as I say, this is building up to last val. There's the thing. Got to the bit there. Yeah, this is building up to, we're going to be building a train controller, a knob box that can drive trains. The starting bit, which is reading this could work with digital and with analog. You may have seen on one of my, I think it was the K3 video, my little test track. Well, that's got, it's an Arduino, not one of these. Principle's the same. One of these rotary encoders, which is used to set the speed. So let's have a little look on here. Clear this. Now what happens? So first click, nothing happened. And that's because the first state was a 0. So now I'm clicking here. And click reasonably. Sometimes it double counts if you click quickly, but I can go down. I click again. Click anti-clockwise. Nothing happened. And the reason nothing happened was because the direction has changed. So I should now be able to take this down to 0. Reasonably controllably. Gone a little bit too far, but never mind. Go back up to 0, like that. That's now a lot more controllable. I mean, it's still, if you twiddle the thing quickly, it moves quickly. Twiddle it slowly, it moves slowly. If you're moving it quick, sometimes you're going to find you double count. But if you're turning it quick, do you care? So that works. So that's actually fairly simple. So the next thing we want to do, I want to look at this and I want to be able to say, we want to put, I referred to this as cap and collar. This is another useful function to be able to do. I don't want O, because I'm going to be saying this is going into a DCC system, so I want the speed to be between -126 and +126, because that gives me forward and reverse. If this was going to go into a pulse width modulation controller for a DC layout, it would be 0 to 255. But the principle is exactly the same with what I'm about to do. So we come in here and we put that in. And all that says is if O is greater than 126, no, it's not, it's 126. If it's less than -126, it's -126. So let's try that. And what that should do is that sets the bounds. We can't go beyond those bounding limits. So let's have a little look. We're nearly at the end of this one, actually. This is fairly straightforward. I didn't want to put this as part of a larger video, otherwise things are going to get a bit too long. But this is reasonably fundamental. So again, first click, nothing. Next click, reads up. So let's turn this up, go all the way up to 126. Turn it around quite quickly. And the thing to note is here, we're not getting any, there's no B's in here. We're not getting any bouncing back the other way. So 126, I'm now twiddling this, and nothing's happening. And it's not that it's reporting the same value over and over again. It's just saying, nah, nothing's happening. Which means this little function down here that says if the value has changed, do something. This would be this is where you write the value out to your train. How are you going to do that? It won't trigger because as far as it's concerned, nothing's changed. If we go back, all the way back. Now this brings up the next problem. This is quite tedious as I'm sitting here playing with the knob. There we are, minus 126. It doesn't go any further than that. Now there's a fairly straightforward way around it. Like I say, you change that 1 and minus 1 to be, say, 5 and minus 5. But what if you want this fine control sometimes? Well, it actually turns out that's fairly straightforward to do. So what we've got up here is I need to add in a little bit more of these. So we go uint 32t, and this is going to be t last O. I'll send this 0 to start with. This is the time. T lost O, T lost plot. This is the time we last changed this O value. So okay, well let's have a look at that. So we're going to come up here and we're going to put this in here. Seems a reasonable place to put it. Uint 32t. Yes, and just a generic t now minus t last 0. We're not doing a check on it. I just want to know how long is it since I last reset this. And we go down here, t last 0 equals get the key right, t now. So every time we go through the loop, we reset that. But in this section here, we now know how long this took. And the other thing we're going to do is instead of doing that there, I'm going to say here, I want int 8t increment equals that. So this increment is now saying plus or minus 1. And then down here, so before the cap and collar, because you don't want to do it afterwards, I'm going to go into here, I'm going to go O plus equals increment. And what I'm going to do is I'm just going to clear that. I'm just going to hit run because I want to make sure that still works and I've not broken anything, is essentially what I'm doing. There we go. Doesn't like that. What have we got wrong here? Last, yes, never mind. Last O. There we are. And that one there. And there I need to put one of those. Try again. See, this is why I do. I mean, that wasn't deliberate. That's just the sort of fat-fingered typing I do on a regular basis. This should work in exactly the same way it worked before. But what I've just by running it, I'm doing a little bit of an error check. So we'll go into here, and there we are. It's working exactly the same as it was, which is what I want. So what we're going to do now is in here, I'm going to put in things. Now, at the moment, we always plus or minus 1. Well, if we turn the dial really quickly, so if the time between the last change, put a heading in here, if we you turn the dial really quickly, so it's 50 milliseconds since we last got a valid value. I'm not going to move it by 1, I'm going to move it by 4. And then here, otherwise, if it was, well, 200 milliseconds, I'm going to move it by 2. And then the default is it'll just move it by 1 if neither of those conditions are true. So let's try that. And away we go, away we go, away we go. As it runs through, has a little bit of a think. I mean, this is a reasonably fast computer, which is why this is quite a quick process. Sometimes compiling can take a little bit longer. So now, turn it nice and slowly. Okay, ready? A little bit faster. So 4, 5, 5 to 9, to 13, to 17, to 21, to 25. It's jumping by 4. So getting it up to full speed is now a lot quicker. And then you've got the fine control when you want it. Turn it a little bit quicker, and you see it's moving in steps of 4. But still get it back down to 0. And that is really about it. I mean, you could put more steps in here. There's code online where you'll see they take this and there's like a curve function for how far to move it. It moves it in fractions, then it rounds it. Yeah, 1 or 2 steps. It's much, much easier. This is also simpler code. On an ESP32, it doesn't really matter. If you're doing this on an Arduino, you might not want to have a huge amount of computationally heavy maths in the middle trying to work out a curve value that's going to come down to, do you add 1, 2, 3, 4, 5 or whatever. Here you've just got solid steps. I could put another one in that says if it's below 120, multiply it by 3. I could put one up that says if it's less than 25, do it by 10, or you could do all sorts. So, I mean, what can you use this for? Now, as I've said, I'm going to be using this to drive a speed controller. But there's all sorts of other things you can do. Oops, sorry, not that. There's all sorts of other things you can do. It's basically just making an adjustment. The key is you can adjust things from multiple locations. This is the absolute fundamental bit. This thing has no idea what value it's set to. The processor does. So something else could tell the processor, that speed that's currently, what are we at? We're currently at -16. I want that speed to go to 0. This thing doesn't know. It doesn't care. I'm going to change that. Oh, it's going to change again. Now this is the obvious function to use for the switch. I haven't wired this up. It will be the same as just a normal button. It's something I'll do before the next step. So when you do that, you can do something. And what you do when you do that could be whatever you like. My little analog speed controller, when you press it, speed goes to 0. Basically because I want to be able to turn the train up to move at a set speed. Oh, it's getting to the end of the track. Stop. You could also do another little bit of processing. If you look as this speed drops, it goes straight down into the negatives. You could put some processing in that says, actually, you know what? When the speed reaches 0, don't go any further. Wait, say a second. So I've got to turn this down to 0. I've got to then do nothing for a second, then carry on. Just to make hitting 0 very, very simple. There's lots of little things you could do. Other little idea, and this is one I had when I was working on this. Time of day. Say this is part of a lighting controller. I mean, you could do one of this. Say, oh, brightness. Make it brighter. Make it darker. You might have a light-dependent resistor somewhere picking up ambient lighting. So your layout lighting is brighter at night, or brighter during the day, rather. And at night, when you haven't got outside light coming in, you can dim the lights down a bit so they're not as bright. But during the day, they're brighter so you can see they're on. You have one of these things that says, yeah, I want them a little bit brighter. Maybe a little bit darker. I was thinking of having something for time of day. Bring up a lighting controller. That, I mean, I'm recording this at 5:45 on Wednesday. To be going out Thursday. So, right, well, I like the layout looks like this at 5:45. Like at 7:15. Like at 8:15. Like 9:15. So you could have a time of day setting that you can just adjust, And of course the clock is ticking the whole time, but this thing doesn't move. This is just, I want to advance it. I want to retard it. Same with volume. You could have automatic volume controls. There's all sorts of stuff you can do with this. The control I've got here, it isn't perfect. It does occasionally miss one. It will occasionally double count. You could, I mean, I've got this thing here in this code. I'm saying, is the value the same as the preceding value? That's what this bit here is. You could go in and say, I don't want it to be the same as the preceding value. I want it to be the same as the last two. Maybe the last three. And there's ways of storing those values. I've just used a single variable. You can actually use something similar to what we've got up here. The problem then is, say you want to go for the last two. Well, I want to make this move. 1, 2. It's going to ignore that. Now it's going to register. That might get annoying. It'll be more reliable, but it'll be annoying. Fundamental principle with model railways. This is not safety critical. This is good enough. So that's how we've got with that. So in conclusion to this episode, which is otherwise going to get far too long, had a little look at the rotary encoder. One possible way of using them, there are many other ways. You can use interrupts. There's a whole load of functions. There's a whole load of libraries. With these little things, I've found actually knowing how it works is useful. I've tried to use libraries, and it's one click. Oh, it's incremented by 4. Because as you saw, there are 4 states between that, and it's incrementing on each one of them. And then you see, but you need to change a value somewhere. Other libraries, that's 1. But you have to change a setting. This is not complicated. A lot of the libraries also, they want to use interrupts. They want to use predefined pins. They want to limit how many of these things you can have. With this code, I could put one of these on every single pin on this ESP32. Yes, I'd have to rewrite the code. They'll all need their own set of variables. You would put it into a class, but it works. Incidentally, you can also get these things that light up. You can get them with red, green, blue LEDs in. There's more pins on them. With my love of blinking lights, you might be thinking, why on earth haven't I got those? The answer is I ordered these before I found out there were lighting ones, otherwise I would have done. But you could have one of these, train control, and it changes colour with the speed. Go particularly quickly, it starts to go green. Go really too fast, it goes red again. There's lots you could do with it. So with a little look at that, we are going to return to this one. This sort of circuit is going to be quite useful. As you can see, there is a screen here. This is going to be part of it. This one has got a proper antenna because I want this to connect to Wi-Fi properly. So we will return to this. This is a little bit of a building block. I didn't want to jump in and say, I've got this. By the way, here's a bit of code. Don't worry about it. So that's that one. A little bit on one of these, how to tame it without any external hardware connecting. Hopefully that might have been at least a little bit interesting, even if you've no plans on actually doing any of this, on just how these things inside controllers work, and possibly why sometimes you'll turn them and nothing happens because the code inside has said, no, that wasn't a valid move. So, yeah. With that, I'm going to leave it at that for this episode. This will be going out Thursday, so I hope you enjoy your Thursday evening and your Friday. Remember, Friday is Saturday Eve. Those of you who have to get up and go out on a Friday morning to go to work, you have my sympathies. I'm lucky enough to work from home most of the time, but yeah, I've been there. I've been that soldier. Right. Anyway, with that, that's enough wittering for this episode. Thank you very much for watching. As usual, likes, comments, shares, subscriptions, suggestions as well. If there's anything else further you want to look at. Yeah, thank you very much, and good night. Twiddle the knob.